So picking up where we left off, remember last time we were talking about galvanic or voltaic cells and how we calculate the voltage between them and what that means. Today we're going to talk about thermodynamically favored redox reactions, which we touched on a little bit last time, and we'll talk about how that's related to the Gibbs free energy or the delta G value for that reaction, and we will talk about concentration cells if we have time. And we'll save electrolytic cells for another lecture. So to start off, we want to talk about what redox reactions are thermodynamically favorable and which ones are not. And this is dependent on the E cell value. If your E cell value is positive or greater than 0, then that reaction will be thermodynamically favorable. But if we calculate an E cell value that is negative, that will not be thermodynamically favorable. Now a reminder, for calculating the E cell value, we take the cathode's reduction potential and change the sign or subtract the anode's reduction potential and put those together, and that gives us the standard reduction potential for the entire system. Here it's telling us that we can use the standard reduction potential table and this equation to determine if any redox reaction is thermodynamically favored. There's another way to determine if a redox reaction will occur, and that's using something called an activity series. And the way that works is the metals are listed in order of their reactivity. I think we saw this in a previous lesson. And if a metal is above another metal, then it will replace it, so on and so forth. But what it's saying is this is an alternate way to determine if a redox reaction will happen, and you simply use the equation from last time, which involves either changing the sign on the anode or subtracting it, and then when you put those together, you're figuring out if the E cell is positive or negative. Positive means that it is favorable, and a negative E value would mean that it is not. Alright, so here is a question. Is the following reaction thermodynamically favored? Okay, so we have barium sulfate, lead, forming barium solid, and lead sulfate. Now, what is being reduced and oxidized here? The sulfate is just kind of hanging on as the anion. Here we have barium plus 2 formed with that barium sulfate going to barium solid. Here we have lead solid going to lead plus 2 in the form of lead sulfate. So these are the two reactions that we pull from the reduction potential table. Now notice that sulfate is not included in these because sulfate's oxidation number is not changing. If you'll recall finding oxidation numbers, if you work through, you would find that sulfur and oxygen, their oxidation number isn't changing. So there's no energy involved in the sulfate transfer. Instead, we're looking at the barium, which was plus 2 on the reactant side, going to barium solid. And then we have the lead plus 2 going to lead solid. These are both being reduced, but we know that's not the case in the actual reaction. So if you look at the actual reaction, the lead solid is a reactant. So we know that this one's going to get flipped over. So you see the note here. We got to change the sign on the lead because we know that's the one that's actually being oxidized. And then we'll put them together. So we still have the negative 290 from the barium because it is going from barium plus 2 to barium solid. Then flipping the lead one to make that positive 0.13. You put those together and it's still negative 2.77 volts. So that reaction is not thermodynamically favorable. This reaction would not produce the movement of electrons. Okay, that negative voltage tells us that it would require that many volts if we wanted to make this go. It's not going to give us that many volts. Okay. Right? How is that then related to Gibbs free energy? Because we know that ultimately Gibbs free energy tells us if something is favorable or not. When it's negative, when Gibbs free energy is negative, that means the process is favorable, and positive meaning that it is not favorable. So let's first look at this note down here relating Gibbs free energy and the voltage. As the Gibbs free energy becomes more negative, that means more favorable, the voltage is more positive. However, as the delta G or the Gibbs free energy becomes more positive, we know that's not favorable, the voltage becomes more negative. So the sign on the voltage and the delta G is opposite, and that is due to this little negative sign in the equation. So if voltage is positive, delta G is negative, those are good, thumbs up. And if voltage is negative, delta G is positive, and those are not favorable, thumbs down. So how do we calculate this using this equation here? This equation will be given to you on the exam, of course, but we need to know what these things mean. So we already know delta G is the Gibbs free energy. Notice the unit here. So important. Because delta G is almost always given in kilojoules. But when we use it in this equation, or remember from the end of last chapter, if we use it in that Ratlink equation, we've got to have it in joules. Okay, so remember to make that transfer. The N here is the number of moles of electrons that are transferred. And this comes from the balanced chemical equation. So when we make our chemical equation, we'll see how many electrons are transferred from the reactants to the products. And that is the number for N. So it'll be a small whole number like 1, 2, 3, 4, 5, 6, something like that. We have Faraday's constant for F, 96,500 coulombs per mole of electrons. So those moles of electrons can cancel in our equation. And then for our E, that's our voltage value. And we know that voltage is joules per coulomb. So that allows our coulombs to cancel and our joules. So all of our units here are going to line up. And that's a little bit hard to see when you're using voltage, but voltage is joules per coulomb. So that'll help things cancel. Alright, so here's an example problem. They want us to find delta G, Gibbs free energy, and they want us to find the equilibrium constant. No surprise, they're pulling in something from last chapter there for the following reaction. So here we have manganese solid and chromium ion, manganese ion, and chromium solid as our products. So we got reactants on the left, products on the right. Here's our two reduction potentials. And remember, one of these has to be flipped. So let's look at the balanced equation. Manganese solid is a reactant in the balanced equation, but it's a product down here. So this one must be the one that gets flipped, because here's chromium as a reactant and also as a reactant. So that one stays the same. So this manganese equation is going to get flipped over, so that's going to be a positive voltage. Then I'll put those together. So this one that doesn't get flipped is the cathode. The one that does get flipped is your anode. So you can think cathode minus anode, or cathode change the sign on the anode. So change the sign or make it positive or subtract the negative, however you want to think about it. And the difference between those two is, I believe, 0.44 volts. And it is positive. So my voltage turns out to be positive, so I know that this is thermodynamically favorable. So I can say that my delta G is going to be negative and my K is going to be greater than 1. Okay, all those kind of run together. Now what we need to do, though, is actually find delta G and find K. Right, so let's go through each of those equations. First off, let's find delta G. We know that our voltage is 0.44 volts. Okay, we worked through that already. There that is shown again. If you want to pause and jot that down if you didn't get it earlier. Once we have the voltage, we can find delta G by finding delta G equals negative NFE. Now the N is the number of electrons that were transferred. So if we look back at our original equations, we have to figure out how many electrons were transferred between these two. So in this one, we have 3 electrons, and in this bottom one, we have 2 electrons. So the chromium is gaining the 3. Remember, this one got flipped, so the manganese is losing 2. You can't gain 3 and lose 2, so you have to balance them out. So look at what they did. They multiplied the manganese by 3, so this would be 6 electrons, right? And they multiplied the chromium by 2, so this would also be 6 electrons. So 6 electrons were lost and 6 electrons were gained. So our N value then is 6. Okay, and they're showing that again here on this later slide. This one got multiplied by 2, so there's 6 electrons. This one got flipped and multiplied by 3, so there's 6 electrons. So the 6 electrons that cancel is your N value, not 12. Okay, 6 were lost, 6 were gained, 6 were transferred. So 6 is our N value. Then we have our F value, which is always the same. And then our E value, or our voltage, which is joules per coulomb. Once we calculate that, we get a delta G value of negative 250,000 or negative 250 kilojoules per mole. All right, so that's how we calculate delta G. Now, recall from last chapter that once we have delta G, we can find K by using negative RT ln of K. We use Kc here if we're dealing with things that are aqueous, or Kp if we have gases. And in this case, we have aqueous things, so Kc is perfect. All right, now we're solving for K. So we rearrange this delta G over negative RT, and then we do E raised to all of that to cancel the ln. So E raised to the negative G, look at this, joules. We have to use joules in these equations. R is our energy constant because it has those joules in it, and our temperature in Kelvin. And look at this K value, to the 43rd power. Huge. This is a very, very favorable reaction. In fact, it's going to be almost totally products by the time we're done. Make sure that you can put this in your calculator. Make sure you know where all these numbers came from and that you can get something in this range for your answer. So what we're seeing here is that if we can find the voltage, then we can find the Gibbs free energy, and we can find the equilibrium constant K as well. Alright, what we've looked at so far is finding the voltage using that standard reduction potential table. And we know that to use that, we have to have 1 molarity for our concentration, our gases have to be at 1 atmosphere pressure, and our temperature has to be at 25 degrees Celsius. But what if that's not the case? What if we are in non-standard conditions? So maybe our concentration is not at 1 molarity. Or maybe our pressure is not at 1 atmosphere. Or maybe our temperature is not at 25 degrees Celsius. That is going to change our electromotive force, or our voltage. For example, just as the reaction runs in general, like for example, if you have a battery and you plug it in and you had some reactants and products in that battery, as the battery goes, your reactants are of course going to decrease and your product concentration is going to increase. That happens naturally. So as soon as you start your cell, it's not going to be standard anymore. Okay? Because of that, the voltage decreases when your reactants decrease. And, of course, when your products increase. So as a battery runs, it becomes less and less effective because the reactants are getting used up. So when the reactants go down, the voltage naturally goes down. Now, the opposite of that would be if you added more reactants to the system, of course, that would make your voltage go up. Right? So the voltage that we calculate is just at standard, but that quickly changes when our cell runs, or if we just add some more, so we don't have 1 molarity anymore. As the cell runs, it's going to run until the voltage reaches 0. And when that happens, the cell is at equilibrium. Now remember, at equilibrium, stuff still moves forward, but it also moves backwards at the same rate. And so there's no force, right? It's just going forward, back, so it's not creating any electromotive force when it's doing that. The concentrations remain constant at that point, even though there's still a net exchange between the two systems. And at that point, we say the cell is dead. Now remember, stuff is still moving, but those electrons are not going to come through the wire with any force to create electricity. All right, here's an example of a system under non-standard conditions. All right, so starting out at the top, we're using this equation. What if the system is originally under standard conditions? So you originally have 1.0 molarity, but you add some more silver ion, so that now the silver is greater than 1.0 molarity. What does that cause to happen? Well, the silver ion is a reactant. So if you put some more reactant in there, that's going to cause the rate of your forward reaction to increase. Think about a reaction. A reaction occurs as electrons are exchanged between these ions. So if you have more silver ions to go pick up those electrons, that is going to increase the force at which those electrons can come in. Therefore, the voltage will increase, or the electron flow can increase. The opposite is true. If you remove some silver ion, let's say you added some chloride in there, and silver and chloride, they make a precipitate, so they just fall to the bottom. Well, now your silver concentration is less than standard. So you don't have as many silver ions to come in and grab those electrons. So the force at which those electrons coming in is going to slow down. The rate of the reaction is going to decrease, therefore the voltage will decrease, and the flow or the current will also decrease. So more reactants, greater force forward, less reactants, less force forward. If this is our voltage that we calculate, we can assume that if we have more silver, the voltage will be higher than this, and if we have less silver, the voltage will be lower. All right, let's think about it for the copper. Now, copper is a product, so this is what we're trying to make. If we have a system that was originally under standard conditions, this copper would be 1 molarity. Standard is 1 molarity for reactants and products. If we then add some more copper ion, remember we're trying to make this copper ion. So now it's like we have too many products. So the rate at which this copper is being made is going to slow down. It's actually going to speed up the rate of the reverse. So the rate of the forward is going to slow, and as that happens, the voltage decreases, and so does the current flow. However, if we decrease the amount of copper right here, so now we don't really have enough products, then we're going to try to make more. That is going to affect the rate of the forward reaction, and that will make our voltage increase. So it's very similar. It's actually using Le Chatelier's principle, if you remember that from equilibrium. If we remove a product, we're going to try to make more of them. So we're going to shift to the right. That's going to make our voltage go up. But if we add a product, we got too much product, that's going to shift us back to the left and make our voltage go down. All right, so here's an example of that. We have a cell that was originally under standard conditions, and it functioned according to this equation right here. So originally under standard conditions means that we were originally at 1.0 molarity for everything that is in solution. Excuse me. All right, and then the cell runs, and as it runs, of course, it's using this reactant and this one to make these products. So over some time, they measured this zinc, and they found that the zinc was now 1.14 molarity. Now remember, it started at standard. So it's gone from 1 to 1.14. It's gone up because it's a product. The question is, what is the gold concentration now? Well, we know the gold concentration should have gone down, right? Because it's a reactant, so it should be used up. But it started at 1. So it started at 1 and it's gone down, but how much has it gone down by? Well, the zinc went up by 0.14. So that's where we get this right here. The zinc went up by 0.14 moles per liter. Right? Molarity is moles per liter. So how much did the gold change? Well, we can use our stoichiometry. Every time you make 3 zincs, you use up 2 golds. So we can use that ratio, 2 golds for every 3 zincs. And we know how much zinc was made, 0.14. So by doing that math, we find that this is the change in the concentration of the gold. It must have went down though, right? Not up. So the gold started at 1 and it changed by that much according to the ratio from the zinc. So we now know that this must be the molarity of the gold. They are both now non-standard. So do you think the voltage went up or down based on that? Well, we can see that the zinc concentration went up, and zinc is a product, and the gold concentration went down, and gold is a reactant. So if we think about Le Chatelier's principle, if the zinc goes up, that's going to shift us back to the left. And the same thing is true if the gold goes down. So these two changes are causing us to have less reactants and more products. So we're shifting our reaction back to the left to try to reach equilibrium, and that is going to cause the voltage to go down. Because the voltage of a system is affected by the concentration, you can actually make a voltaic cell or a battery with the exact same metal at the anode and the cathode. If you did that, if you think about your reduction potentials, you'll have your reduction potential for the same metal at the anode and the cathode. So you're going to be taking that same metal and flipping it and adding it to itself. So your standard reduction potential is going to be 0. However, you can use the concentration to create a potential difference. So the way you do that is you make the concentration at the anode less than the concentration at the cathode. So you create a really high concentration at the cathode of cations and a really low concentration at the anode, so that the electrons want to flow to the cathode. So you're creating a potential difference by creating a difference in concentration. As the reaction proceeds, you're going to see your reactants go down and products go up, and eventually your concentrations will be equal, and then your battery will again be dead. But this is the way a lot of batteries are built. Instead of using 2 different metals, they just use an extreme difference in concentration at the cathode and the anode. So here's an example of that. You have nickel at the cathode and nickel at the anode. You still have your electrons flowing from the anode to the cathode. They're just flowing from nickel to nickel. But what is making them want to go over here to this other side? The reason is because on this side, on the cathode side, you have nickel concentrated. So you have tons of nickel plus 2, and all these nickel plus 2s, you can imagine there's millions of them in here, every single one needs some electrons. So the electrons are coming over this way. And then at the anode side, you don't have much nickel plus 2 at all, so there's really no attraction for electrons down here. So the electrons will easily leave the nickel solid and go over here. Now, as they come over here, they're making nickel solid, and so eventually you're going to use up these nickel ions. And then over here, you're making nickel ions. So you're going to use up this nickel solid. So eventually these nickel ions will be equal on both sides, and then your battery will be dead again. But we can recharge it, right? All we got to do is hook it up to the wall and send those electrons back over there. And change our concentrations again, and then the electrons can flow back the same way. So what this is showing us is that the non-standard cell can take a standard cell that would be 0, right? Nickel and nickel, that potential should be 0. And we can use concentration gradients to build up voltage to create a potential difference.